So it's kind of an area that I've been working on for quite some time now, trying to use the crystallographic information contained in your atom probe data to help spatially calibrate the reconstruction. So I've just got a little example picture here of this is a nickel-based superalloy, and if you go and reconstruct that in IVAS using the default reconstruction parameters, you get something like this. But then by looking at the crystallographic information, like the known plane spacings and all that, you calibrate the ICF and the KF, and then you get something like this, and you can just already see visually that it's quite different. So yeah, we'll just be going through how to do that, and yeah, and why that's important. Yeah. So why is reconstruction calibration important? Well, I like this figure that comes out of Baptiste Gold & Co.'s textbook that they put out in 2012. That basically shows that depending on the image compression factor, the field factor, or the KF, and the detector efficiency, you get quite a different resultant reconstruction. And so if you want to do absolute spatial measurements on your reconstruction, so if you're doing like a proxygram or 1D concentration profile, and the distance part of that, the absolute distance part of that is important, then it's in your interest to go about trying to do a reconstruction calibration to fine tune that. So, but I also want to make the point that you can't always do the crystallographic reconstruction calibration method in which I'll sort of be showing today. Sometimes there just isn't enough information contained within the data, depending on basically the material properties of the material that you're trying to run, as well as the experimental parameters that you've used. And yeah, so it doesn't mean that your data is like garbage or junk if you can't do it. But you just have to be mindful that if you are going to be doing measurements, that you have to be a little bit careful about the numbers that you're quoting there if you can't go about doing this procedure. And this is basically another slide kind of showing the same thing. We've got these user-defined reconstruction parameters, mainly the ICF and the field factor. If you look at the equations relating to the tomographic reconstruction, some papers from like Baptiste Gold and the Barr paper, you can kind of see that the spacing between your lateral coordinates is proportional to the image compression factor over the field factor, and then your in-depth increments are proportional to the field factor over the image compression factor squared. So it's basically the relationship there, and we'll show the full equation a little bit later. But I just did a sort of a matrix here of different image compression factors and field factors, and then reconstructed them all. And as you can see, they look quite different. But number 2 here is the crystallographically calibrated reconstruction, and is the more spatially correct one there. So to do crystallographic calibration, obviously you need to have some crystallographic information contained within your data. And so I like this slide here from my previous, like my co-supervisor while I was doing my PhD, Michael Moody, and I think Baptiste Gold may have contributed this too. But this is pure aluminium data set. We've got the field evaporation image here, which is basically your first port of call in actually seeing crystallographic information. As you can see all these lower density features, which we call zone lines and poles. You can even actually start to see some terrace rings coming out of this pole here. And so already there's quite a bit of information contained in there. And then if you go about and look at the corresponding reconstruction, and if we just take a slice along this zone line, you get this. And then you can see around these pole features that you actually start to reconstruct individual lattice planes. And so from this, it's obvious that there's quite a bit of information contained in there. And the idea is, well, can we use this to spatially calibrate? Yeah, so we can use the known crystallographic relationships. So you sort of need to know something about the crystallographic nature of the grain before you go about a reconstruction calibration. And so from all the great work that's been done with, XRD, X-ray diffraction, in electron diffraction to some extent in the TEM, there's whole databases of information on crystallographic, measurements, lattice parameters, and all that kind of thing. And you have to use that to enable you to actually calibrate your atom probe reconstruction. So how do you go about reconstruction calibration? Well, most of you here, I imagine, will be using IVAS or AP Suite 6. And so if you're using that, then basically at the final step of the reconstruction wizard, you can click on the Expert tab and then click on Reconstruction Explorer, and that opens up all the options for you to look at spatial distribution maps along a particular pole, and do the calibrations and things like that. And so I'll be showing you how to do that. So you can also use other third-party softwares, of course. So you can go on to something like MATLAB if you've got some reconstruction code. So I tried to share some code with you, so hopefully you've got access to that. Actually, Peter Felfer wrote it. I've stolen it from him. But it's a nice bit of code, and that's really a good template on which to develop further refinements in the reconstruction calibration, and do a lot of testing and do things that you wouldn't be able to do on IVAS. For instance, if you wanted to go through and sweep through a whole range of reconstruction parameters, that's something that you would want to use some programming software to do. And that's just a zoom in of the information there. So I sort of mentioned at the start, there are actually three parameters, or three main parameters. So you've got the image compression factor and the fill factor, and then the two main ones that we need to calibrate. But it's also worth considering the detector efficiency. The detector efficiency is sort of an easier parameter to nail down because it's usually constant for the instrument that you're using. So for the current multi-channel plate detectors used on the CAMECA leaps, so there's been a number of studies over the years that have tried to independently measure those detector efficiencies. And so here they are. So if you've got a LEAP 3000, 4000 reflectron, you're probably getting a detector efficiency of about 0.37. If you're lucky enough to have 5000 with reflectron, you're getting about a 0.52 or 52% detector efficiency. LEAP 3000, 4000 SI, so the straight flight path is about 57. And if you've got a 5000 straight flight path, it's 0.8. And so as most of you would realize as well, there's been a new atom probe that's, a couple of new atom probes that have just been released by CAMECA. So I'll have to update these slides. But as far as I know, the detector efficiencies of those new instruments are similar to the 5000. So I think they're using the same microchannel plate. So for the straight flight path, around 0.8, maybe a little bit less because of the some fancy stuff they do with the ion optics. But we'll have to test that and work out what that value is. So basically, that stays constant for your instrument, no matter what material that you're going to be running on. So for the instruments we have here at Sydney, we've got straight flight paths, LEAP 3000, 4000 SI, so I'll be using 0.57. So the first thing to do is to basically look at your field evaporation image and look for the crystallographic poles and zone lines. And so I've just got a legacy data set here, quite an old one that I collected during my PhD of a high strength low alloy steel. And we're looking at ferrite. So this was collected on the 3000. It's using 25%, 25K, so very cold, as cold as we could go, and 25% pulse fraction. So generally with those conditions, you're going to be able to get better crystallographic information. So yeah, the colder you can run it and voltage pulsing, the easier it is going to be to crystallographically calibrate your reconstruction. That being said, that's usually at odds with sample success rate. So it's about trying to find a balance. So you may want to increase the temperature a little bit, or even use laser pulsing so that your sample or specimen, can run better. But yeah, not so much that you just lose all this information completely. So like I said, this is ferrite. It's a body-centered cubic structure, and it's when you're going about doing your indexing of your poles, it's important to know the space group of that crystal. And so for BCC, it's number 229. And so that'll become a bit obvious when I show you Winwolf, actually, and that we can use this stereographic projection software to actually try and help us index the poles. Yeah, so when you use that software, you can get a stereographic projection kind of like this and overlay it with the image. And then the idea is it's a bit of a manual process still, although there's been a bit of effort to automate this, but basically manually just trying to align those patterns with what's on your detector. So I'll also note that the projection on the detector isn't exactly a stereographic projection. So Baptiste Gold wrote a paper a couple of years ago kind of going into the details of that. It's actually closer to an equidistant azimuthal projection, but it's a good enough approximation, at least up until 5,000, I would say, to help you index the poles. With the newer atom probes, with the Inviso, which has a larger field of view, it's going to get more important to actually get that projection more accurate. Otherwise, yeah, it's just going to be getting more difference between the projections. But as you can see, it's a pretty good match up there. And then we can then identify what these poles are. And so I've just identified them there. So the field of view for the up until about between the 3,000 5,000 leap series is around 60 to 70% usually. If you haven't overfilled the detector. Older 3000 models are actually a little bit less than that, probably sort of 40, 50 degrees field of view. But yeah, that's also important to know when you're trying to index the poles. Yeah, otherwise it's going to be hard to match up the patterns. And I'll also note that, as we all know, that sometimes the poles and zone lines are quite difficult to see. And I was going through some of the reasons on the previous slide. It's to do with the material properties as well as the conditions that you've run it in. But there are some techniques in which I've been working on, and others as well, to help extract clearer pole and zone line contrast. And we'll go through a little bit of that soon. So when trying to calibrate the image compression factor, so that's basically your next step. So you've looked at your field evaporation image. Usually I should mention as well, usually just for like 1 to 2 million atoms within the center of your reconstruction or your data set, sorry. Usually you wouldn't select the whole data set because the position of the poles changes because your image compression factor doesn't stay constant. So you're better off just taking a smaller slice, and then you'll get a clearer image. Otherwise, it's going to blur out. But once you've indexed those poles, then you can go ahead and try and calibrate the image compression factor. And so we can calculate the detected angle between two crystallographic directions. So we usually call that theta prime. And it's kind of like this. If you imagine your tip and you've got your flight path here, and then you think of two poles in your detector, yeah, you can work out what this angle is using this equation here. So for our instruments here, we're using a flight path length of 90 millimeters. So you'll probably also note that, so this is assuming, it's a simplifying assumption that this is a right angle, and that's not exactly right. It's slightly off a right angle, but it's a good enough approximation in most cases. But we can fine tune that by, making that a little less simple. But that's usually what we use, or what I use. and it usually gives a reasonable result. So that's the measured angle there. So we can also calculate the theoretical value between two crystallographic, or the normal to two sets of crystallographic planes, and we can just use the dot product equation here. So if we're talking about these two poles that represent the 011 and the 013 planes, and we're trying to find them, so we're trying to find the angle between the normal to those sets of planes, we can just substitute in, and then it comes out as this, and then you just go ahead and solve for theta. So your image compression factor is really just the theoretical angle between those two directions divided by your measured angle. And so that equation I've taken out by a publication, which I'd all recommend you to read, from Baptiste Gault on advances in the calibration of atom probe tomographic reconstruction. So we have a spreadsheet that we use, and so I'll be going, you should have a copy of that as well, and I'll be going through with you how to use that. That you can then essentially enter some of these measurements from the detector into that spreadsheet. So you enter your flight path, you enter your crystal information, because this is ferrite. We know the lattice parameter here, it's cubic. So, you know, ABC are all equal, alpha, beta, gamma are all equal as well at 90 degrees. So you just enter that in there. And then you go through and then you enter the XY positions on the detector that the poles are at, and then the Miller index of those directions. And here, when you're entering the Miller index, it's also important to use how's the best way to describe this? Like the highest index planes along that direction. So I haven't used this plane here, but for instance, 001, so the 001 direction, I probably should have had a little bit of a diagram here, but if you imagine that in BCC or FCC, you've actually got that central plane in the unit cell. So you'd be entering 002 to just account for that plane spacing. That becomes important when you go through and try and calculate the field factor. But anyway, you enter the Miller indices and the XY positions of those. And then on the spreadsheet, it automatically will just calculate the image compression factor between all combinations of those poles, and then calculate an average of those. And we can see we get a little bit of a distribution. But usually you're looking for, you can check the residuals. You generally want it to be sort of less than something like 0.2. And that's a good indication that you've indexed correctly. So if it's more than that, then you've probably indexed the poles incorrectly and you have to go back. So there's all these sort of checks and balances you can do through the process. Yeah, so there is a bit of variation in image compression factor, because the image compression factor itself doesn't stay constant across the whole detector space, and yeah, it doesn't stay constant through the experiment, but it stays roughly, it doesn't change hugely, but it will change. So it's something to keep in mind. So this is sort of like an averaging sort of approach. I'm mainly going to be doing the procedure for like straight flight paths, but I will just make a note here that the procedure that we're using is basically the same for reflectron fitted instruments. But with the reflectron, usually take a flight path length of 40 millimeters. And so the best way I can kind of describe that at the moment is that it's sort of more of a displacement between your tip and the detector, and the displacement, yeah, between the end of your tip and the detector after it's come around the reflectron, that's roughly around 40 millimeters. And that seems to work reasonably well. So that's just what I'll say about that. Anyway, once you go through and do all that, once you go through and do all that, you'll get a final calibrated image compression factor. And that's it. Then you can move on to then work out the field factor. So the first step is that we build a temporary reconstruction using the default value. And so in IVAS or AP Suite, it's 3.3. And so I'll just kind of quickly mention here, this was probably covered in one of the earlier lectures, but the field factor actually comes about from this equation, this sort of electrostatics equation, relating the electric field and voltage to the radius of the tip. So if you were trying to evaporate from a perfect sphere, you wouldn't need the field factor, but because we've got a hemispherical cap and a truncated cone, we have to have this other factor. Some people even go as far to say a fudge factor, but it's what makes the relation. Yeah, it's what basically makes the relationship between field, the voltage applied, and the radius kind of work for your geometry of your tip. So I'll just say here, in many reconstructions, yeah, crystallographic planes can be observed perpendicular or near perpendicular to the Z direction. So yeah, across about that sort of 60 to 70 degrees field of view. Yeah. So when you go into your Reconstruction Explorer, you'll see something like this, and then what you do is you just come to this region of interest box here, and we're just trying to locate a pole region. So usually we take an outer radius of about 4 millimeters, and then we set the X and Y centers to the center of the pole that you're seeing on the field evaporation image. The ion sequence range, if you just selected a ion sequence of 1 to 2 million atoms, usually actually I would change this to 100, and the ion sequence center I would keep around 50. So the ion sequence center is just basically, so if you can imagine taking a region of interest cylinder kind of around your pole, you're just taking the center of the spatial distribution map calculations from the center of that cylinder in Z. Anyway, you can go through here, and then when you're reconstructing that cylinder, I suppose, of ions that have hit at that pole, we just take the X projection center and the Y projection center as the center of the pole, the same as you did when you selecting the region of interest here. Then you generate your spatial distribution map, and then hopefully you get something that looks like this. So with the spatial distribution map, we're histogramming the interatomic distance between all the atoms in that region of interest along the Z direction. And yeah, if you've got lattice planes in there, you should get something that looks like this, where the peak-to-peak distance is representing the interplanar spacing, and yeah, the peak heights are sort of a measure as well of the strength of crystallinity as well. So if we just go back to our example, so the plane spacing along the 011 for this BCC ferrite, so it depends on KF. So there's equation again from that paper that I mentioned before, from Batt's paper. Yeah, it looks like this, and you've got all these different parameters in there. And so at this point, we've basically pinned down all the free parameters except KF. So the atomic volume, the flight path length, the field, the detector efficiency, the area, the sort of detector area of the experiment, the image compression factor, and the voltage. So all that remains is this. So yeah, we go through and try and work that out. So so we want to make, so when we get, so the correct value for the field factor will correspond to the correct, yeah, a value for the plane spacing along 011 equal to the theoretical value. And so you can use this equation here to work out what the plane spacing for that set of planes will be, just using this equation, which most of you will probably know. But it's also important to keep in mind that this only works for cubic lattices. Things get a bit more complicated when you go to hexagonal, close packed, or any other type of crystal. Good thing about the spreadsheet that we've made is that it basically can solve for the general case, not just this specific case of the cubic crystal. So as long as you enter in your ABC, alpha, beta, gamma, you can work out what those plane spacings will be. But then we incrementally adjust the field factor to attain the correct crystallographic plane spacings in 3D reconstruction using the following equations. So your plane spacing will be proportional to your field factor squared. And yeah, we can use this equation here where we have a measured plane spacing from our SDMs. We know what theoretical plane spacing is. We have an initial KF, and then we solve to find a corrected KF. But yeah, the spreadsheet sort of automatically does that for you. But those equations, again, are coming from this paper. So after you've gone through and done that, it's good to just check the ratio between the theoretical and observed plane spacings. And so you want to be seeing something close to 1. So that's the point. We're trying to calibrate to that theoretical plane spacing. And as we can see here, they're all very close to 1, which is a really good indication that we've indexed the poles correctly and that we've calibrated the reconstruction correctly. So that's basically the process. So I think probably it'll make more sense when I go through a bit of a demonstration of how that's done actually. But that's essentially it. But you know, is there a better way? And yeah, of course there is. There's more sophisticated ways in which you can go about it, and there's been various works over the years that have tried to do a better job. So one thing that's worth mentioning is a dynamic reconstruction, which takes better account like the change in the image compression factor and the field factor through the experiment. And so this is just an example here from another paper from BAT. I think they're looking at a steel here, and they're just measuring image compression factor and field factor through the iron sequence range or through the experiment, and you can see that it changes a fair bit. Well, sort of about, what is it, like about a 0.2, 0.3 in a image compression factor, and the field factor is changing by, yeah, about 0.5, 0.6 through the experiment. So not like huge, but yeah, it is changing. And so basically do the same procedure, but then you're just updating yeah, the image compression factor and the field factor through the experiment. So to do something like this, you would need MATLAB or Python or something like that. You can't do this on IBAS. But the problem with this is that it takes significantly more time. So it's more a matter of whether you can be bothered to go and spend the hours of time to manually slice up your data set and measure the ICF and KF for each slice. But there's you know, approaches that I and others have been working on to help automate that. So there's automatic indexing processes. I think on IVAS now, there's a procedure there that's working similar to what they do in indexing Cauchy diffraction patterns in EBSD using like Hoff transform and things. This is a method where we've tried to use machine learning using a neural network to automatically index poles. So that can speed up the process of that. And then there's also ways to automatically track the pole movement for a measurement of the change in image compression factor. So yeah, this process could be sped up for a more dynamic approach. So one of my colleagues here, Alec Day, has also been working on a new protocol of a dynamic type of reconstruction, which he's calling crystallographically mediated reconstruction. So I just wanted to point that out, and there's just some references here, some papers that you might want to check out about that new protocol as well. It's yeah, trying to sort of streamline this process. And just a few tips before I finish off and jump into a bit of a tutorial. So what do you do if you can't detect crystallographic information within your reconstruction? So there's other methods available. So you can use features within the data set. And I think the presentation after this one will go into more of the detail of how that's done. So here you have some platelets, and there's a known angle between what those platelets should be. And so you can adjust the reconstruction parameters until that angle, that known angle matches, matches the one that's reconstructed. There's also different types of procedures that you can use to enhance pole and zone line contrast in your field evaporation images. And so I've just got an example here of this was from a pre-sharpened silicon microtip array. Here's our field evaporation image. We can clearly see we've got a 004 pole in the center here and some clear zone lines, but it's pretty hard to work out where the other poles are. And so you need at least 2 poles to get an image compression factor. So yeah, using kind of, can't go into the details of this too much, but by basically doing localized reconstructions at different voxels along the detector space, and then doing spatial distribution maps or fast Fourier transform through the corresponding reconstruction relating to those voxels on the detector, and then measuring the crystallinity strength, you can get maps like this, and you can start to pull out more information about the poles. And so here we can start to see these 113 poles come up much clearer. And then from there, you can go ahead and then be more confident about an image compression factor measurement. And this is sort of newer attempts at doing that. So I'm about to put out a paper on this actually. So stay tuned for that. But it's an example where we were looking at this additively manufactured, so electron powder bed fusion produced Inconel 738 nickel-based superalloy. This is a field evaporation image, one of the early attempts, where we're running in voltage mode, but at a bit of a higher temp, around 50 Kelvin. And as you can see, we can't really see much in that field evaporation image. But if we drop the temperature to about 25 Kelvin, we're using a perceptually uniform color map. Some information starts to appear. So if we just look at the density across the detector, we see something like this. Then if we filter that detector map for nulls, which is the number of pulses between evaporation events. So if we look for detection events, if we just filter for detection events where there's been a short number of pulses between the next ion has been detected, we can get something like this, and we can start to see, oh, we can pull out some zone line information. And so that gives us information about the symmetry of the crystal there, and we have a much more confidence now that, oh, we can see this 4-fold symmetry around here. This must be our 001 or direction, but 002 when we consider the higher index planes along that direction. And yeah, we can play around with filtering of nulls. If we look at a large number of pulses between evaporation events, we can turn on the poles a bit clearer. I've also been playing around with methods to look at the distance between successive evaporation events, and that proved to be quite useful in extracting crystallographic information here too. And then the crystallinity signal maps, similar to what I showed for the silicon before, is shown here. Can't go into the details of it, but yeah, it's a more optimized method. It's running faster. We're using a different way to measure the crystallinity strength. And we're also taking advantage of the ordered structure of the aluminium atoms here, because it's gamma prime, and yeah, it's an ordered phase. So yeah, we can see that we can start to pull out much higher index poles than what we could see in the original field evaporation image. And this is the final indexing. So if sort of all else fails or whatever, you can also look at correlative methods to get some crystallographic information about your tip. So, I think it's always preferable to directly use the crystallographic information contained within your atom probe data and not rely on correlative methods, because the correlative methods still won't give you information about image compression factor, for instance. And sometimes it's difficult to align the correlative method with the atom probe data. So here we've used transmission Kikuchi diffraction. So it's basically EBSD, but in transmission mode. This was on a aluminium bicrystal. We did this at the Max Planck Institute. And yeah, we can see that we can basically do it's a like an inverse pole figure map kind of thing here, and yeah, and then we can get information, for instance, the misorientation across that boundary. But yeah, we still can't use that to actually work out the image compression factor and the fill factor. So just a few other points. So in general, pole zone lines will be clearer with voltage pulsing, usually using a pulse fraction of around 15–25% and at lower temperatures, but this often results in high risk of specimen fracture. So if that's an issue, you could try running your sample briefly under better conditions for crystallographic info. Maybe just try and switch on the voltage pulsing for 1 million atoms and then switch back over to another condition, laser pulsing, for a high success rate. And I think with the newer atom probes, not with the Inviso, but I think with the LEAP 6000, you can do some more sophisticated swapping between voltage and laser pulsing. So there may be some opportunity there to sort of get the best of both worlds, so to speak. So just in summary, so the reconstruction procedure that I just went through is what I'd call like a static type of reconstruction calibration. So where we're just using a constant ICF and KF for the reconstruction. But as I've pointed out, the reconstruction parameters don't stay constant. So a dynamic reconstruction calibration is better, but it's slower. So it's really just a matter of how accurate do you need your reconstruction to be. I mean, for most of the reconstructions that I do, I'm still just using the constant ICF and KF. I would rarely go to the length of doing a dynamic reconstruction just because of how time consuming it is. And if you're trying to do, for instance, a measurement around a grain boundary, well, maybe you just want to calibrate the reconstruction in close vicinity to that grain boundary, you know, and it's not such an issue if it's slightly off to the extremities away from that boundary. Don't be afraid to use MATLAB and Python to access more crystallographic info. So really, you can just do, you know, an infinite number of things to your data. Yeah, a lot more than what you could just do with IVAS or AP Suite. I'm happy to share code. You should have access to a little bit of code, and I know Peter's got some of his own code, but just reach out if you want some code from me. And I'm trying to get my code out onto GitHub more and more, but to sort of a work in progress. And yeah, there's some recent developments in this space, and I'm just pointing in the direction of some papers from my colleagues Alec Day and Anna Figuera, who've written there. And just for further reading, of course, there's the Atom Probe textbook from the group here at Sydney, and then Dave Larson's book also has some good stuff on reconstruction. And the paper, you know, you should read the seminal reconstruction paper from Barr et al. And then I was referring to this paper a lot through the presentation as well. So the advances in the calibration of atom probe tomographic reconstruction by Bat and co. Yeah, that's a really good read as well. And so there's a couple of new ones here as well that are worth looking at, that are going into more of a dynamic kind of protocol. And so yeah, that's it for the Prezzo. So are there any questions before we move on from here? Oh, there's a few in the chat. Oh, okay. Martin said he's going to send the spreadsheet. Oh, Rob's in here. Yeah. Okay. Yes. So that's good confirmation. So I think there's going to be some good opportunities there, actually, being able to swap between voltage and laser pulsing, and also having the wider field of view in the Inviso is going to be great as well for this kind of stuff as well. So really excited to extend these methods to the new generation of atom probes. So so now I'm going to jump into the tutorial on the reconstruction. So I'm going to use AP Suite 6. Okay. And so hopefully most of you have access to that. And so what I've already done here is I've just opened up a couple of data sets that we can look at into the Reconstruction Explorer. The first one that we'll look at is just a pure aluminium data set. So, you know, maybe not so interesting from a material science perspective, but we still use technically pure aluminium a lot. This is a sort of archetype example to develop a lot of our crystallographic analysis and reconstruction protocols that we're developing. So it's a really good one to develop things on. So we'll start with that, and we get a lot of crystallographic information, so it's a good one. Let me just check which data set I want here. So it's the 537. Okay, so we're going to start with this one. Okay, so it's just the pure aluminium. This is also a very old legacy data set. I think this collected on our 3000 a long time ago, over 10 years ago probably, but you know, it will serve its purpose. So like I said, I like to just select like a couple of million, 1 to 2 million atom sequence, usually from the center. I'm going to actually select here because there's actually, there was some like drift or something in the experiment around here. So basically I'm just considering about from here to here as the experiment. So I'm going to take here, and then I'm just going to commit that. That's roughly, I mean, it only has to be approximate, 1 to 2 million. That looks about right. And we click next. We'll get something like this. You can't see much yet, right? But then you've got to unsample the data, and then boom, it's crystal clear. And then so what I would do at this point is take a screenshot. So just take a screenshot of this. We'll get out of there. And what I like to use is free software, which I'd recommend you get, called WinWolf. It's a really nice little stereographic projection software package. It looks like this. So we want to look at the stereographic projection for aluminium, and aluminium is FCC. And so if you don't know what the space group is, you could just, what I sometimes do, a quick thing, is I just go on like web elements or something. Web elements, and then aluminium crystal. Okay, and then it pops up, gives you a really good summary of the crystal information there, the crystallography, and yeah, we can see that it has space group number 225, and it goes through and gives you your lattice parameters as well, which come in handy later on. So we'll go back to that. But at the moment, we just need to know that space group number. So we select that up here. So we'll go to 225. I'm going to select a smaller D-min just to show a lot of poles, because it'll make the projection a bit clearer. And so you're going to get, there's your stereographic projection of FCC, aluminium. Now I'm going to take, I'm going to open the field evaporation image in the background. So it's here. And so that's what we got there. And now I'm just going to try and fit the patterns, basically, yeah, try and fit the stereographic projection onto the field evaporation image pattern. So, you know, it's not that easy to see, but you can, you know, increase the pulse here. Like I said, for this, yeah, for this type of atom probe 3000, we're looking at something like 60 to 70, probably a little bit less than 60 degrees field of view actually, because it's even older. And I think I maybe overfilled the detector here. So we can just zoom in, and it's a bit hard to see, but you've got these great circles on the stereographic projection, and each one of these represents sort of 10 degrees, well, 20 degrees across the whole circle. But, you know, so yeah, you can count out sort of 9 circles out to, you know, 180 degrees full field of view. So we're only going to go out to about like 3 circles, and we should be sort of roughly somewhere in close proximity to where we need to be. So we can see this nice pole right in the middle here. We've got a nice 4-fold symmetry. So I'm pretty confident that that's going to be 001 or 002 when we take into account that we're using the higher index for the smallest plane spacings along that direction. But the direction is 001. And we can put that there, and then I can set rotation axis to just lock that in place. And then I can just rotate until these patterns look like they roughly match up. So So just from before. So this process can take a bit of time, right? Like even for the clear field evaporation images like this, it's sometimes not super easy. So I know that this pole up here should be 024, just from what I did earlier. But so yeah, okay. So I'm just going to rotate that around until that matches up with that up there. And I'm going to zoom in a bit further. So yeah, our angular field of view on this is actually pretty small. It's more like 50 degrees, but that's probably because of overfilled, or possibly this was even on a really old detector on the 3000 where the field of view was even a little bit small. But yeah, if you're using a modern 4000, 5000, you have an overfilled detector, it's probably about 3 to 4 of those circles across, so 67 degrees. So yeah, as you can see now, those patterns are pretty well aligned, right? So you sort of just, you get the hang of it, you get the knack of it after a while, and you kind of see, okay, yeah, look, all these dots are sort of matching up, like these lines are matching up with these zone lines, and yeah, I'm pretty confident that I've got that indexing correct. So it takes a bit of practice, and you're probably going to make mistakes, but there's a few little checks you can do when you're trying to calibrate the reconstruction to make sure that you've indexed correctly. But then I just make a note of what these poles are. So we've got our 001, but I'm going to change that to 002 to account for the plane spacing along that direction. This is 012, so you can read it off the top here. But I'm going to change that to 024 because for FCC, we've actually got another, you know, it's half that plane spacing along that direction. If you're not sure, a good little reference, I might just pull that up. Oh, little reference is in the back of the Atom Pro textbook from Sydney. So in the appendices there, you'll find, so BCC, so if we just go to FCC, it'll list all the planes, and it'll already taking into account like the structure factor, if you like, or the higher index along that direction. So yeah, you see how 002 is listed here, 024 is listed, 224, yeah, so not 114, not 012, if that's making sense. So yeah, you can look to the back of the textbook there, or you can, there's other ways in which you can do it, but yeah, maybe, but it is sort of important that you do that. So anyway, we know what the poles are now. Oh, which one? I've got a few of these open. Yeah. So yeah, we know that's 001, 012, and we're going to take 113. So I just make a note of what they are, and then I go back into AP Suite, and then I switch on the pointer position, and then I just record what those XY positions are for the poles. So I'm just going to write them down. So 02, XY, got minus 3.67, minus 4.36. And then this is our 024. This is 3.03, 21.66. And then this is our 113. And then this is going to be 17.72, 9.18. Okay. So now I can actually, at this point, go into my spreadsheet. So here's the spreadsheet that we use at Sydney, and you should be able to get this, and we can start filling in that information. So I knew that for this experiment, I was using flight path length of 90. That's also, if you're not sure as well, that's shown in the first step of the reconstruction wizard. So you can just read that off. So it's 90 straight flight path. And so here's where you enter the crystal information. So if you forget, you can just go to web elements, or, you know, even better if you've got like crystallography text. But yeah, this is in picometers. We're going to change that to nanometers. So it's going to be 0.405 for ABC, and then just 90, 90, 90. So add that in. Okay, so we've got our flight path and we've got our crystal information. Now we put in the pole information of the field of operation image. So I'm just going to enter in those values that I jotted down. So first pole was at minus 3.67, minus 4.63, and I'm going to enter 002, not 001. Otherwise, the KF, the calculation isn't going to work out. So the next one was at 3.03, 21.66, and then 0.24, not 0.12. So using the higher index there. And then 17.72 and 9.18. And this is going to be 113. And then the spreadsheet just automatically goes through and works out the image compression factor for all combinations of those. If you want, you can enter a false pole. But for the interest of time, I'm just going to leave that. So a minimum, you only need a minimum of 2. I could have done this just with 2, but it's always good to use a few more. We go over here and we have a look at our image compression factors that are calculated of all this information. We can see here, so for the AB pair, so between 002 and 024, we're getting about 1.58. And then if we go between the A and C pair there, so 002 and 113, we're getting 1.6. And then for the other combination, 1.6. So you can see they're very close, right? Sometimes they're not that close. That's like particularly close. But you want to basically be between sort of 0.1, 0.2 difference, and have a bit of confidence about that measurement. Yeah, like I said, I mean, there's ways in which this could be refined. I mean, like I said, we're using this simplifying assumption of a 90-degree angle when we're calculating the observed angle between the poles. You can fine tune that a little bit to probably make this calculation a bit more accurate, and there's things that could be done. But anyway, it gives you a good sort of overall average across the detector. So try and use poles that are going, you know, across as much of the detector space as you can, I would say, if you can. But yeah, generally that works pretty well. So I'm pretty happy with that, right? That's looking pretty good right now. So I'm feeling like I'm confidently like index these poles correctly. If these were way off, if I was getting like an ICF of 1.2, 1.8 for another one, I'd be like, oh, I think I've done something wrong. So I'd have to go back, check my stereographic projection overlay and see if I made some mistake with the indexing. So I'm going to take that. So we see that the initial default ICF was actually 1.65. So this has changed a bit, right? It's now not that much, but it's gone down to about 1.6. So there's a bit of a difference there. So we can go now back into AP Suite. Can jump through. So I'll just go through these pretty quickly. I suppose other presentations will cover the mass calibration and mass spectrum aspects of atom probe reconstruction, but yeah, we're just going to be focusing on the crystallographic aspects. These are automatically identified, so we just got, yeah, it's just pure aluminium with, yeah, maybe a little bit of hydrogen in there, but yeah, from the chamber. But that's it. So that should be okay. And then, oh, actually, maybe I do need to. Let me just select these. Okay. So for it, I'm going to. Okay. Just wasn't ranged before, so it's automatically ranged now. So that's looking good. I mean, I think that's fine. You know, you can tweak that, but if you like, but that's close enough. Oh, I think here I do have to slightly change it to sort of go to the next step for some reason. Yeah. Okay. Now I can go next. Okay. So we get up to the final step in the reconstruction. Got our information here. So I'm going to now change the detector efficiency to 0.57. which was sort of independently measured, a long time ago on that instrument by Bad and Michael. So yours, if using a straight 5 pass 3000, 4000, it's probably a little bit higher than 50, somewhere between 0.5 and 0.6. So now I'm going to change the image compression factor to what we calibrated here. So I'm just going to go 1.6. So take that off. We're using flight path length of 90. Now we're going to be calibrating the field factor. So we click on Reconstruction Explorer. It comes up. So we select our region of interest. Like I said, so we're selecting a region of interest around the pole of interest. So we're going to start with the 002. And usually I take an outer radius of about 4 millimeters, somewhere between 2 and 4. If there's not a lot of signal, sometimes it helps to go, actually a smaller radius. Maybe not, maybe signal is the wrong word there. When your crystallographic information in reconstruction is maybe not as well reconstructed, sometimes it's just better, closer into the center of the pole, although then you're getting less atoms. So maybe your noise levels go up. But anyway, you can play around with that a little bit, but usually I'm using between 2 and 4 millimeters radius around that pole. I'm going to change the center X and Y positions to the position of the pole and the detector. I'm going to change the ion sequence range to 100. Keep the ion sequence center at 50, apply. Then change the reconstruction parameters. So I want the projection center actually down the pole. So I just change that to the center of the pole, same as the region of interest. Okay, and then we can just click generate for the spatial distribution map. So the histogram along the projected Z direction. So the histogram of interatomic distances between all the atoms along the projected Z direction. Well, actually it comes up along the X direction, but we're going to look down the Z direction. And so we can see we get a beautiful spatial distribution map. Unfortunately, it's usually not that clear. But hopefully you get something looking like this, where you get some sort of like signal like this, and then so you've got a central peak here, and then so the peak to peak distance is representing the reconstructed plane spacing, right? So usually what I do is I won't just take the first peak and look at this distance. I usually go out a bit further to just sort of take away any sort of measurement error there, right? So it's the first peak, second, third, fourth, fifth. I might just, the sixth one looks nice and sharp here. So I'm just going to take the sixth one. We can see that it's around 0.636. So I go back in here, 0.636 divided by the 6 planes, and that's our observed plane spacing. And now we can see theoretical and observed. It's quite different. It's almost double. The theoretical is almost double. It's actually a little bit higher than I thought it was when I did this earlier. But anyway, we'll see how we go. So we go through and do the others. So just double checking I didn't put anything wrong here. Should be okay. Yeah. All right. See how this works out. 3.03. So now we're looking at the 024. Okay. That's what we get. As clear as it's pretty clear there. It's pretty clear. Yeah, you can see that you're picking up some planes there. But it looks a bit different to when I was doing this earlier, but hopefully it'll sort of work out. So we can, so that's our central peak. That's first, second, third. I might just go out to the third one here, actually. 1, 2, 3, just because it's getting a little bit noisy. So I'm going to take a 0.156. I'll take 3 for that one. Okay. So there's a little bit of a difference between theoretical observed, but it's not too bad, and the calculated K factor here is pretty close. So I think I'm going to assume that that's all okay. And we're going back in here, and we just do the final one. So now we're looking at 113, so 7.72. 9.18. I hope I had Z focus for. Yeah, and that looks super clear as well. Yeah, so you can see you're clearly getting the planes there. So we carefully look for the central peak, and then we count out to a couple of peaks or whatever. So yeah, we can go 1, 2, 3. This is a nice sharp peak, 4. So I'm going to select the 4th peak there. Have a look at the center of it. 0.284 divided by 4. Yeah, and then it comes out like that. And then so it looks at the average calibrated K factor for all those sets of planes, and then just gives you an average, and it's saying, okay, your field factor should actually be 4.4. So it's a bit higher than 3.3 actually. So I'm going to go back and then check that. So I'm going to take that off, and then change the K factor here. What did I say? 4.4, right? 4.4. And then do it again, and hopefully our plane spacings will match up pretty closely with the theoretical plane spacings. So basically repeat the process. Go back over to our 002. Okay. Oh, that's right. You can see here as well that the planes are really well reconstructed. So let's grab some water. And we generate a spatial distribution map. You can see already that the plane spacing is much larger now. So that's good. So 1, 2, 3, 4, 5. Let's just go out to about the 5th one. I'll take the highest point here, 0.94 divided by 5. So okay, so that's looking good, right? So now our observed plane spacing is very close to the theoretical. Theoretical and observed is, it's only 1.07 sort of thing. So yeah, and then we can go through and then do it for the rest of the poles. How are we going for time? We don't have a lot of time. So maybe I'll leave it there, but basically you just go through and you do it for the other poles, for the other sets of crystallographic planes, And then hopefully the theoretical and observed all looking close to 1. And if it's all looking close to 1, then you're pretty confident that you've indexed correctly and that you've calibrated correctly. And then you get the final ICF and KF output. So here it's saying, okay, just fine tune that a little bit. So you took 4.4 here, maybe it's closer to 4.6. So yeah, so you can go in and then you can just adjust that. Let's say it comes out as 4.6. I might just jot that down. So what I'm actually going to do at this point is I'll make a note of what my calibrated ICF and KF are, 1.6 and 4.6. Then I go back, select the whole reconstruction that I want, because I want to avoid this drifting or something that happened here. And so I just select all of that now. You can see that. We probably should do this again. Just wait for that to go through. It's doing the voltage and bulk corrections on the mass spectrum there. Okay, it's done. Come here. I might just select that again. Yep. And then that looks all good. For some reason I need to just slightly change the range for it to go, or confirm the ranges or something, and then click next. I get back up to this step, and so I'm just going to put in our calibrated parameters. This one was 1.6, so, and then this one I was actually changing all the way up to 4.4 or 4.6 actually, I thought. And yeah, and then that's, I guess, what I would call like a static reconstruction calibration for this data set. So then you just create your preview. Here you go. You can save the reconstruction. Actually, I forgot to do something. So one of the things that you might want to do for like subsequent analysis on your data set, right, is to actually access like an EPOS file. That might be changing in the future as we're sort of migrating more to HDF5 sort of formats. But anyway, based on the IVAS sort of system, you create your POS file, and then you could create an EPOS file, and that gives you access to a larger amount of data per iron hit, right? So you've got the detector XY, the voltage, standing voltage pulse, the number of pulses between the evaporation events nulls, and so on and so forth. So it's good to have access to that information to do a whole bunch of different types of analyses. And one of the ones that it's good for is if you want to play around with other reconstruction procedures, because it saves the detector X and Y. So I think to do that, you have to just adjust some of the, yeah, this is it, the APT sections. You have to select what's saved in those when you save the reconstruction. You don't have to select all of them. So yeah, you just have to work out which ones you need to actually generate the EPOS. But yeah, anyway, So that's what you have to do. And then you can export the EPOS file from AP Suite 6 for a subsequent analysis in MATLAB or something like that. So that's what I'm going to do now. I just wanted to quickly show how we could sort of access the reconstruction or play around with reconstructions in MATLAB very quickly in the next 20 minutes. So here we are. So I've opened up MATLAB, and you should be getting access to a couple of scripts and functions, which I and others have written. So the read EPOS was written by BAT quite a number of years ago, Atom Probe Recon by Peter Felfer, and SavePOS by BAT as well. So actually none of them written by me, but I build a lot on, particularly on the Atom Probe Recon for other things. Like say if I want to cycle through ICF and KF and just see how that's changing very quickly. It's much faster to do it on this than to try and do it on IVAS or AP Suite. So first thing to do would be to read in the EPOS file of that data set. So here's one I created earlier of that same Aluminium data set. So it's the EPOS file here. What you can do is, so if you just got your editor window open and you make sure that this script or this function is actually in the read path. You can, if you click on home in MATLAB and set path, you can make sure that that function is in the read path, or that function has to be in the folder in the current folder. I don't like putting the functions in the data sets in the current folder because I'm using these functions for like many different types of data sets, right? So it's just, I don't want to keep repeating, putting the same function into every single folder. So I keep them separately in their own folder in my MATLAB scripts folder. So yeah, I just have to make sure it's in the set path. Otherwise, MATLAB won't be able to read it when I'm in this current folder. So I just copy that in there, and then I just want to put the file name of the EPOS there, and then just going to press enter. Hopefully that runs without error. It should. So there it goes. So it's reading in all our data. So here we can have a look at the workspace. We've got our detector X, detector Y, our mass to charge ratio of all the ions. Pulses. I'm getting tired. I can't exactly remember, but number of pulses in evaporation events. Yeah, I don't know, voltage DC, voltage pulse, XYZ reconstructed. And, yeah. Oh, this is, I think, to do with multiples. Yeah. Anyway, whatever. It's all ready now. The ones that we're interested in are the detector X and detector Y, and to do the reconstruction. So if we go over to the Atom Probe Reconstruction Code, so this is also a function, but you might have to adjust some things in here depending on what you're looking at. So you have to adjust the flight path if that's changed. You have to adjust the detector efficiency if that's changed. You have to adjust the specimen parameters. So here I've already inputted the values for aluminium. So you have to know the atomic density of atoms in nanometers cubed for the specimen that you analyzed. Here it's kind of simple because it's just pure aluminium FCC, and you can just work out, okay, you've got 4 atoms in the unit cell, and we know our unit cell length is 0.404. So it's, what is it? It's like 4 divided by 0.405 cubed, and then you get 60.24. We have to know our evaporation field for aluminium. And so, you know, this is another area that's, you know, could be improved on and is being improved on, I think, with DFT and stuff to get these evaporation fields for different species more accurate, particularly in sort of multi-component systems. But we know that for aluminium, it should be pretty close to 19. And so IVAS and AP Suite sort of take these in automatically. But here you have to set it manually. And then it just goes through and follows the reconstruction procedure that was basically outlined in that paper from Baptiste Gold that I showed in the presentation. So basically just have to, again, take this. I'm just going to save, because I've already got XYZ of my IVAS or AP Suite reconstruction. I'm just going to save this as a new XYZ. You don't actually have to use M, right? Because M's not going to change. It's just the X, Y, Z that we're reconstructing here. So just change the name here. It's actually dx, dy. The voltage, you have to be a bit careful here because it's a voltage pulse run. Our voltage is actually going to be a voltage DC plus a voltage pulse. And then KF and ICF, I can use what I used before. It's going to give a reconstruction very close to what you get in OVA for AP Suite. Not exactly the same. So I think there's some additional tweaks and things that have been used in AP Suite that haven't been implemented here, but it should get you pretty close. And it's just a really good template to sort of work off and build on if you're interested in this kind of thing. So I think that's all I need to do. Hopefully that runs through pretty quick. So that's done. So it's reconstructed. So we can visualize that in MATLAB if we want, maybe just quickly. So I might just say here, 3. I'm not going to plot all the atoms because it's too many. I'm just going to quickly look. Okay, what have we got in here? We've got like 9 million atoms. So I want to maybe plot every 10,000. Just so it doesn't freeze on me. I don't want them. I just want to plot a dots, right? So that's what I put there, and then I can set the color to whatever I want for this. You know, for a multi-component system, it gets a little bit trickier, right? You got to maybe plot. You set up a little script, and you would and plot each atom separately. You'd hold on to the figure and plot all the atoms separately. But here we've just got aluminium. So, well, actually, I might just keep that blue. Hopefully that'll work. It didn't work, and the reason it didn't work is because I didn't change these to Y and Z. Actually, yeah, okay, so that worked. So that's our reconstruction. And then you can adjust it a bit. You can say keep the axis like axis equal, so it's not sort of changing as you try and rotate stuff. And it's I guess scale. So yeah, so that's your reconstruction there. So and you can adjust that to suit. You know, you can put the labels on. Just to give you a bit of an idea of the kind of things that you can do. X label, I think it goes like this. So, you know, if you're doing quite a lot of these, you would write a script to do this. You wouldn't just be entering it in like I'm doing now, but, you know, just to show you how. There you go. So, you know, you can label the axes, do all sorts of things. Add transparencies or, you know, isosurfaces even. I think Peter's got code to do isosurfaces. Maybe he's already shown you how to do that. Okay, and that's it for that. So I think that's mainly the stuff that I kind of wanted to cover. I had another data set that I had. I mean, we've got 10 minutes, so we probably won't finish it, but maybe I'll just pull up another example on AP Suite in the remaining time. So we switch now over to a HSLA steel data set. So we go back into the reconstruction wizard. Not as pretty a voltage curve here, but it's to be expected for a multi-component alloy, and it's a much larger data set, this one too. So I just sort of looking at it's already at 20 million. So we're going to around here or something like that. Will give us about 2 million. Yeah, just approximately, because we just don't want the poles to blur out too much if we select too large a sequence. This, we'll just unsample that. Take a screenshot. Oh, what happened there? Getting a bit tired now. It's okay. I think I've already got it saved on my desktop anyway. So we've got that. I'll just close these. I'll open up the morph again. You can check on web elements. I'm going to change these lattice parameters a little bit because it's a bit different, because it's not just iron, right? It's steel. But I've got, you hopefully know something about your crystal structure before you put in the atom probe. But anyway, what I was interested in is the space group number. It's 229. So for CC, you just select that. You select zoom in 0.1. Get that up. You open a background image with this one. Increase the spot size there. You often get this kind of weird sort of, it looks like a lolly wrapper or a bow tie type shape for 011. So for steels and stuff, I often use that as a quick way to just sort of like know straight away, okay, that's 011, right? And then I sort of go from there. So you can use those little hacks and little tricks. So where's our 011? Yeah, that's an 011, but yeah, I'm going to use this one. And I'm going to center that on that. I'm going to zoom in first to our field of view, which will be, I know this one's really kind of small actually. So again, old data, I think I overfilled the detector. It's usually a bit larger than this, but anyway. Gonna put that there. It's actually even a little bit further in, I think, something like that. About 50 degrees field of view for this one, which is pretty low. But, let me just check this. I want this one in 121. Oh yeah. Yep, I think that's about right. Yeah. Yeah, sometimes it can take a while to. I'm looking for the 031 pole. Something. This is it. Okay, so I'm just going to move that around. So I'm going to adjust the zoom a little bit. Yeah, okay, that's looking like a slightly better fit. So you see how it's all kind of like the patterns are kind of matching up. So you just try and get them to match up. So at the moment, it's still a bit of a manual process. And, there's ways in which this could be automated and improved as well. And there's the automatic indexing on AP Suite, and I've asked that works quite well when you've got a really clear pattern. But yeah, if you've got a little bit less signal and things, I think it still works quite well to do something like this. But yeah, so, and then from that, now we know what all these poles are, right? We can click on them and work out what they are. And then we can then go back into AP Suite. We take the position of those. I'm not going to get time to do it all, but let's just take down this one, 011 XY, so 12.6 minus 14.52. I'm just going to open the one I did earlier. Yeah, so the value is actually put in here a little bit different because I chose a slightly different position in the experiment, right? It's pretty close. This is saying 12.71. I just recorded 12.6 there, right? So it's just changing a little bit through the experiment. So that's what I mean, that, yeah, it's more of a static reconstruction. It's very highly calibrated around that 1 to 2 million slice, it's going to deviate slightly as you go away from that. Usually, I think that's fine. If you want something super, super accurate for the whole reconstruction, you'd have to go through and do a dynamic, which could take a long time. Hopefully one day it'll be more automatic, but yeah, at the moment. So yeah, we just sort of enter in the spreadsheet like that, but just to sort of show, you can go through. Just to show you that we can in fact get like a spatial distribution map on that pole and how that works again. Yeah, this is going to be a bit. Yeah, so this is a multi-component alloy, right? So it's going to take a bit of time. So I'm not going to go through and index, identify all the peaks, but I'll just do the main iron ones. I know this is manganese. I'm just going to leave it there for now. Okay, and that's range there. I think I just have to adjust one of these peaks for some reason, go to the next step. Go change that to 0.57. These are our default reconstruction parameters. Click on Reconstruction Explorer. Go to the pole. Let me change the projection center to the center of the pole as well. Oh, I should have left some time for questions, I guess. But anyway, yeah. And so there we go. We've got a really nice spatial distribution map down the pole. And yeah, we can go out to one of these peaks and then measure the plane spacing, and then just do that for at least 2 poles. A few more is better. And then you get, you calibrate your image compression factor. So you calibrate the image compression factor of the sort of distance between the poles. And then when you're doing all this with the spatial distribution maps, you're calibrating the field factor. So yeah, I think I might just leave it there. I think that's about time. So yeah, I hope you guys learned something from that.
Yeah, I'm fairly sure everyone has learned a lot from there, and got an idea how to do crystallographic calibration of atom probe data sets. Huh? So essentially, when we calibrate reconstructions, what we always want is we want something that we know about the sample. And one thing that's actually fairly reliable is the sample's crystal structure. There is no really realistic scenarios where if you have an aluminium sample where the lattice parameter would just deviate magically in your sample from that of pure aluminium. I mean, it might differ a little bit. Or you all know Vanguard's rule, for example. Yes, it might differ a little bit, but it's a fairly solid way to actually identify something you know. And the good thing about it is it's in the volume, so it's kind of everywhere. Because other things, you might just be some information you have locally. Maybe you know that there is a precipitate somewhere, or you know that there's a grain boundary somewhere. It's just local. It's just at one spot in your data set. But if you have a material that's a crystal, the crystal is everywhere. Andrew is still here?
Yeah, I'm here. Yeah.
So
it's all sounding good.
Now it's your chance to actually ask Andrew whatever you want. Any questions from the audience?
Hey Andrew, impressive work. I just have
Hey,
one
Martin.
very quick.
Yeah,
It's Martin talking. Sorry, I did not
Oh,
bother to raise
Martin.
my
Sorry,
hand.
I thought it was.
Yeah, no,
Yeah,
very
sorry.
very impressive work. And I was just wondering, when you decide the location of the detector of individual peaks, you're just roughly estimating by moving your mouse over the pole. Have you or do you have an idea how much this really changes if you are not really in the center, or is it fairly good enough to just have this rather rough estimation?
Yeah, no, it's a good question, and I've thought about that a bit too. And it's not going to make much of a difference. It's only going to make a very small difference. Like I think any efforts to make things more precise and like consistent is always a good thing. So and it is a bit of a manual process at the moment, right? So there is a little bit of a human sort of element to it. And yeah, I think as we get more automated methods and things like that, it'll get more and more precise. But yeah, at the moment, like if you're roughly in the center of the pole, a little bit off, it's going to make very little difference to the final ICF that you calculate. I think a little bit. It will make a bit of difference, but yeah, just try and get in the center. And
okay, yeah. Thanks.
I would have a question that's maybe not going to you, Andrew, but I can see that already Rob Alfig and Dave Reinhardt are in the chat. So all of what we've talked about so far was really, wide-angle atom probes where you can assume that, all of the atoms are somewhere landing on a hemisphere. And, everything is kind of even just shifted by the angle that the atoms land. What was actually necessary for the Invisio atom probe to change there? Is there anything you can comment about that, or is there anything, any information that you've put out in a paper or somewhere that people can look up and maybe have some reconstruction going for that as well?
Yeah, not yet.
I think
give me a little bit of time.
Relevant for you, right?
Yeah. I mean, probably. I think Rob's on here, isn't he? He probably can answer a bit better. But no, not yet. So but it's exciting times here at Sydney. We're basically coming to the end stages of the installation of the Inviso, and yeah, really interested to dig my teeth into some of the data and to work out like how some of these protocols might change with the new atom probe. But I know that we're going to have a larger field of view, so that's going to be great. So we're going to get more crystallographic information as well as many other things, right? You're able to capture, your whole tip or very close to your whole tip and see, things like FinFETs and things much easier. And yeah, heaps of reasons. But one of the things that I'm interested in, of course, is that we're going to get more zone lines and pole information. And so that should make machine learning type methods of indexing easier, and just a bit more confidence in indexing the patterns. And so, yeah, I'm looking forward to that. There's also the voltage and dual voltage laser pulsing type stuff with the LEAP 6000. So it'll be interesting what comes out of that in this space as well. I think there'll be some, interesting opportunity there. We've got this digital beam laser capability, deep UV. We should get better success rate. And from the field evaporation images I've seen coming off that, they look really good. Like they look, just as good as field evaporation images from voltage pulsing. So this old rule of thumb that, you can only do this kind of thing with voltage is, I think, going away, right? Like it's becoming easier and easier to use. Yeah, it's going to be fine to use laser pulsing to do this with the new generation. So that's great. And that opens up a whole new array of materials that don't run very well in voltage pulsing, of course, to do this kind of analysis. Yeah. So I don't know, that's an answer. But yeah, of course, we'd like to get some papers out soon about new capabilities on the new atom probe, for sure.
There was actually a comment from Rob in the chat where he said that a similar electrostatic model approach for reconstruction is used in the Invisio 6000 as in the 5000 XS, which I assume means that they have some kind of model of what the sort of to correlate to connect the detector coordinates on the physical detector with sort of the launch angles from the specimen, which I think is a very sensible approach. Okay.
Yeah, I think it'll be the same approach. It'll just, probably a higher compression factor, but the process itself shouldn't change too much. Yeah.
Okay, so thanks, Andrew. Thanks very much for your input. And we'll now move into a short break. And after the break, we'll jump into a reconstruction calibration using objects.
Sorry, I would just have a quick question.